Hello, I'm happy to be here. I love Devnexus, one of my favorite conferences in the US. And today we're going to talk about design patterns for multi-agent systems. And the whole nexus of this, presentation was me basically getting bombarded with confusion every time I try to build a complex multi-agent system. And like Rod said, kind of forgetting some of the lessons of the past in trying to build something completely novel, and then forgetting that we went through this whole thing many times over, the last 30 years. If you were into the SaaS explosion, we learned a lot of different patterns of basically how to make those deployments work, and how to make them work at a fundamental level. And they hinged on things from the past too. So with Gen AI, one of the things that we like to make fun of Python is that they came from this world where enterprise doesn't exist. They came from Jupyter notebooks, and then when you try to take that knowledge and turn it into something that runs in a Fortune 50 company, it just collapses on its own weight. So this talk, it's about that basically, trying to surface some of those patterns and apply them, hinging on the lessons from the past. I am Brian Bodden. You can reach me at bsb@redis.com. Send me an email for anything that you have doubts about Redis or agentic memory, or basically how to making your RAG systems faster. And you can find me on Blue Sky and GitHub. And I'm a part of the Java Champions group, which has been an honor. So today's agenda, it's going to be talking a little bit about agents, just very briefly, but talking about the agentic pattern landscape. What patterns are evolving, what patterns are coming back in style, and how to basically classify them, how to apply them. And then we're gonna get into the meat and potatoes of the talk, which is basically 3 different sets of pattern groups. One of them is gonna be routing in tools and memory. The other one is gonna be multi-agent coordination. Then we're going to talk about goal-oriented planning, which is basically in Babel, if you were at Rod's talk. And then we're going to talk about having, one slide, basically, to give you a little bit of where my mind is in terms of making decisions when it comes to building the systems. So let's start with what an agent is. And it's a simple question, but it doesn't seem to have a simple answer. Let's go with the dictionary definition. It's basically, a guiding intelligence to achieve a result. That's probably the vaguest, but actually most accurate one, because the moment you try to pinpoint it down, you're gonna be like, oh, edge case. And also you taint it with your implementation specifics. Again, the word comes from Latin, and it's to do. So agents are doers. And they've been part of computing since the 1950s. So an agent should produce, or it's capable of producing an effect. So if the agent just sits there and doesn't do anything, it's like the tree in the forest thing. It should be able to act for or in place of another. And this actually, it seems like a very lightweight concept, but it's very important when you apply agents to things like agentic assistance or enterprise workflows. So either the agent it's yourself automated, or it's a completely different persona helping you achieve a specific goal. And when you conflate those two, bad things happen. So this is lessons learned from enterprise customers that have chatbots, which basically they look super simple on the surface, but under the iceberg, there's basically ERN systems and all legacy systems and COBOL databases and paid for SaaSes and stuff like that. In that context that is being rehydrated for your chatbot, it has a lot of complexity on how to retrieve that data. So RAG actually has become the super complex thing that everybody thinks, oh, it's just a chatbot. It's like, how hard can it be? An agent should have the means to basically guide that intelligence that it's available now to produce a result. So let's talk about some of the things that agents should do. Autonomy, so they should be able to operate without direct intervention of others. Like Rod said, with chatbots, we kind of give them a crutch by having the human in the loop on every part of the loop. It's not like we're just, now they can basically go for a long periods of time, but there's still a window of time when they basically start collapsing. And I think that some of the latest benchmarks, it's like something like 8 hours or something like that, I don't know. But after that, they start doing things that you're like, whoa, that is questionable. So that is something that the whole industry is working on, to basically having this long horizon of activities that an agent can do without basically collapsing under this kind of entropy that basically builds up. So social ability, interact with other agents and humans. This one is actually a fun one. Basically, with patterns like the Blackboard pattern, you can basically have an agent, and this is kind of similar to all queuing systems, where an MQ series would put basically a message for a request in a queue, and then the right worker will look at the signature of that message and be like, oh, I can do this. So it's something similar like that, but it's basically the ability for agents to communicate with each other and satisfy specific needs of another agent. There's a whole movement right now of basically giving agents wallets. Yeah, scary. And the whole crypto world in blockchain is jumping into that. I think Stripe has a proposal of basically how to provide a wallet to an agent. So, for example, when you're doing something with a specific assistant, it would basically ask a set of MCP tools. It's like, hey, what's your SLA? Can you provide these things in sub-millisecond performance, and what's the cost? And basically do a negotiation, and given a range that you give them, say, yeah, I'm gonna go ahead and pay for this service for the day, or something like that. And as long as the SLA continues to be upheld, it will continue basically doing that. So yeah, this is getting very, very interesting. E-commerce is gonna change radically in the next few years. So reactivity, and this is kind of like the robot view of an agent. They should be able to have, sensors to basically feel what's going on in their perceivable world. And by sensors, in the case of just software-only agents, they could be events. They could be something that drops into a message queue. They could be an SSC event. So, the typical things that we basically react to in software environments. And proactivity. Now, and this is kind of very tied to what Rod was talking about, basically. A goal-oriented behavior. Being able to see a set of conditions, create a plan. Maybe the goal that you give in the agent, it's something very grandiose. But to get there, the agent will have to create its own sub-goals that basically get you closer to that specific end state. In planning. Planning, again, this is something that we've seen evolve in agents like Claude Code and stuff like that. At some point, we were working with Claude Code, and then it's like, hey, here's a checklist of things that I'm gonna do. And you're like, oh, that's new. And that really changed, basically, the game of how long they could go and how accurate the end result could be. In adaptability, we have LLMs. LLMs, like I keep on mentioning Rod, like Rod said, they basically are non-deterministic systems. You might have same prompt, different results, change the temperature by 0.001, and the whole thing goes bananas. So obviously we need to put a lot of guardrails in there, but that same non-deterministic behavior allows us to have them be able to adapt to different novel situations that we didn't plan for. So again, agentic systems, and if you're like me, I'm an ESL kid, and basically then they said, oh yeah, agentic, that's a new word. I'm like, that's not a word, it's not in the dictionary, But hey, we have to live with it now. So agentic systems are networks of autonomous agents that interact, collaborate, and sometimes compete to solve problems. The competition part too is actually pretty cool. If you guys have heard or read about reinforcement learning, that kind of comes into play when, and it's normally done at the LLM level, but now it's being done at the agent level, where you can basically have, obviously, agents learn from their mistakes, but also simulate a bunch of different paths before actually doing them. So it's kind of like the draft mode of something, and then figuring out, of n number of drafts, which ones are the most feasible or the most prone to basically win the race. So again, all of this stuff, it's not new. There's a lot of history when it comes to agentic patterns that we're using today. One of the big ones, it's BDI, which is belief, desire, intention. Basically what you know, what you want to achieve, and basically how to go about it, and how to kick the ball down the hill to basically, that's not a saying. But again, this is from like 1987. So yeah, I don't know. God, 87, wow. Like, I don't know, Lethal Weapon, Flashdance, pretty old. And then we have Inception, we have SOAR, State, Operator, and Result. These are all bases of knowledge that were used in multi-agent systems before LLMs. So let me be clear, multi-agent systems existed for a long time. They were just really hard to write. They were bound to basically rule engines, expert systems, homemade algorithms to figure out, decision points. And now a lot of those architectures are coming back, and we're ripping out some of that extra super, million lines of code complexity and throwing an LLM in there with a gigantic problem and saying, good luck. So those systems back then, one of the biggest problems were that they were very hard to debug and figure out what was going on. And it was still just code, if then else's, all over the place. Now we have this thing that basically, lives at the pace of its own, or the beat of its own drum. How many of you have written a RAG chatbot and then swap the model and get completely different results? Okay. So yeah, this would be like the equivalent of basically saying, oh yeah, I just replaced my spark plugs and now my car is flying. It's like, what the hell? So yeah, it's a very different world. So guardrails, protections for all these things are paramount. So yeah, the LLMs came in and basically, kind of try to do the tablecloth trick, and all the China went flying. So one of the things that we've been seeing in the industry, this is just from, I believe, March of last year. So it's in AI, in machine learning, in data science, this is all news. So things are slightly better in some areas and slightly worse in some others. But yeah, this is like Rod said, these systems are not doing well at the enterprise level. The most basic ones that are like chatbots are doing okay, mostly because we can actually really emphasize the human in the loop in them. But the ones that basically are UI-less or with no interaction with a human, those are not doing that great. They're doing better than they were in March, but they're not doing that great. And why is that? My thesis is that, again, it's a lot of Python being thrown into the enterprise. I worked in environments where somebody would give us a gigantic Jupyter notebook, and it said, here's the system, it works. Yeah, on a markdown document. And then we would have to try to turn that into a runnable system. And then you figure out that things don't scale, things basically have all kinds of race conditions, there's no shared state. Well, there needed to be one because everything was linear in a notebook, and it's easy to be like, oh yeah, everything works fine. There was no threads, none of the things that we know basically cause problems when you try to scale systems and make them reliable. So, agentic systems must provide control layers to harness the LLM's power and basically control that unpredictable behavior. Those reasoning capabilities are amazing. We can do things that we never could before, but we have to be able to rein in all that power. So the hidden complexity. Back in March, that's from that same paper that I showed in there, the failure rates were 75%. So that's pretty bad. That number, I believe it's lower now, but still. So yes. Oh.
You keep saying back in March.
Oh, March of 25.
Okay.
Yeah. So again, 75% failure rates. And the causes, and this is an important one to keep in mind. Specifications, obviously being able to tell the LLM basically what to do. In that, again, it's prompt engineering and now context engineering. And the problem with that is that it's very LLM specific. The moment that you add guardrails, who are you gonna have judge the LLM? The LLM? So basically having things like LLM as a judge helps, but then you're spending probably now twice the amount of tokens for that. In OpenAI and Sam Altman, it's getting richer and richer. So how do we deal with this? Then inter-agent communication. That also, it was pretty catastrophic back then. But now we have things like at least structure outputs, where we can at least say, hey, this is a formula, this is a template of what the output that you produce is, and this is how to consume it to another agent, and it becomes a contract between two agents. So things are better in that respect. But still, how many of you have had a structure output that basically now filled in with garbage? It happens to me all the time. Sometimes, let's say there's a float that's supposed to be in that spec, some kind of JSON document, and the agent or the LLM decided to basically put some other, a hex number or something in there, and you're like, what is going on? And that seems to be basically very spiky behavior. There's no, in my case, no way to trace it. What caused that? Nothing in the prompt has changed. Nothing in the data that came in has changed. Even if you write integration tests, you will, talk about flaky tests. Tests in the LLM, in the age of LLMs, are super flaky tests. So disobedience. Obviously, we all dealt with this one. I'm a pretty fiery type of person. I have a kind of a dynamite personality sometimes. And I have never been so angry at something inanimate. Other than, I don't know, my microwave sometimes, the dishwasher. Oh, this is a pattern, yeah. But I have yelled horrific things that I would not say to another human, to Claude Code or Codex or Augie. And my wife, it's in the other room going like, what is wrong with this guy? And have I made poor choices in life? And information withholding. Sometimes an agent decides that another agent doesn't need to know, and that seems to be actually the one that is actually growing in concern, where now the LMs are getting smarter, but that smartness seems to make him. And I feel that they try to basically charge you more and do less. I don't know. There's got to be something somewhere in there in those weights that it's doing something funny. But yeah, information withholding seems to be on the rise. And interventions are not enough, basically. Improving the prompting gives you about 14% more. And there's systems right now to basically do reinforcement learning with multiple prompts, test them all, evaluate. Even if you do that, you basically just get 14% out of basically advanced prompting. So Dijkstra said it best, and this is kind of in preamble to the frameworks we're going to talk about. So we're going to talk about Spring AI, LangChain4j, and Babel. And again, the idea is that, again, abstraction is not to be vague about something. It's to just think at the right level to basically deal with the problem at hand. So, there's some things that you need to basically do C code for because you're dealing with registers in LAUs and, things at that hardware level. And there's some other things that you can do with Java. And there's some other things you can do with Ruby. So that abstraction level, it's very important when it comes to basically dealing with agents. Sometimes you are at the wrong abstraction level and you're basically building a lot of little primitives that are already encapsulated in a bigger pattern in some other framework. So just because you chose something, don't die on that hill. It might be too low level or too high level. So you have to really evaluate that. And, you can combine them too. So, You can have an application that has Spring AI, LangChain4j, and a Babel, all in the same, which is what I did with this demo. So given all of this, and I don't want to give you nightmares, but I'm from the, a group of 4 days, no, gang of 4, sorry, and then the J3E blueprints. And I'm going to preface this by saying that implementation techniques, design patterns are not Legos. You're not supposed to basically try to assemble the biggest collection of them to build a monstrosity. They need to be used in the right place. Sometimes they might not be already encapsulated in something. Sometimes you have to implement them yourself, and you should implement them at the right level of abstraction. Otherwise, you're going to basically end up with, remember all the manager classes we used to have in J2EE? Like pretty much everything had a manager class, and we decided that everything needed to be a mini framework, and then you end up with so much code that by the time they fire you, nobody could basically fix the system. So for the agentic patterns landscape, I started basically collecting some of them. In this image, you can see that the ones that have the little hourglass are ones that are coming from basically workflow systems, rule engines, basically old school mass systems, multi-agent systems from the past, even from the world of COBOL. There's some patterns in there that actually will apply. Also, from enterprise, basically distributed computing. All the things that we learned scaling microservices, some of those things still apply, actually apply more than ever now. Nowadays, we're still building our agentic systems in a very monolithic way, in creating very heavy units of compute. And eventually, we want to basically go into this more like a swarmy, small agents that can do very, very precise things in a lightweight fashion. So this map is growing every day. When I build something, I'm like, well, this looks like that thing that we used to do. So yeah, we're using that pattern in here. And again, this might be a little bit of a rehash of what's already in your minds, but I want to refresh your memories and make sure that you basically bring those back into your agentic systems. So let's talk about the demo that we're going to talk about today. So we're going to do a demo that basically uses 3 frameworks. Spring AI, which basically gives you this very nice composable building blocks. And we're going to cover routing, handoff, tool use, MCP tool use, agent memory, and generator critic. Not all in super detail, but they're in the actual implementation. LangChain4j gives you like this declarative AI services. So it's I would say a little higher level than Spring AI in a specific API of LangChain4j. And then in Babel, which is I think the highest level of abstraction in here, which is basically goal-oriented. A lot of discovery, a lot of basically, this is the ultimate goal. It's like a declarative environment rather than a more imperative environment. All right, so the domain, it's e-commerce. And I found a data set called OList, which is a Brazilian marketplace, kind of like the Brazilian Amazon aggregator of products in purchase and reviews and things of that sort. It has 100,000 real orders. It's a Kaggle data set. And I created a curated subset of that, obviously. I didn't want to load all that data into Redis for just a demo on my laptop. But as you can see, we have customers, we have orders have items, a typical e-commerce thing, but there's reviews of those. We're going to basically be using a lot of the reviews to make a lot of decisions. So it's an incident response system. And on the AI part, we're going to basically do the customer intake and then do routing, basically what agent should handle this specific request. And then lookup of data using tools. So a lot of the data, all the data is stored in Redis. And we created an MCP tool to basically talk to Redis to get some of that data. Actually, I use a Spring framework called Redis Ohm to basically create the tools that basically do the querying of the Redis database. Then for demo number 3, we're going to do an intervention planning, which is more of like, hey, here is this collection of agents, and let them all work in combination to come up with a resolution or a plan to address this specific seller shortcomings. All right, so the application architecture, it's I think fairly simple, given the only part that is a little problematic is I had to separate everything into services because I didn't want to mix everything, all the code bases into a single one, so for demo purposes. So there's a Spring AI application that has the UI. There's a LangChain application service running on port 8882 and the Embabel on 8883. They are all talking to Redis using MCP. There's also a Redis MCP memory server, which is a Spring version of our Python memory server, which I wrote in Spring because nobody tells me no anymore. But yeah, it's basically the idea is that you can use memory as an intermediate blackboard to basically share knowledge between entities. And I have Rafael here, it's going to have a talk on agentic memory, so you can see how crucial that is for agentic systems today and in the future. Oh, and obviously we have the LLM providers down on the right. So let's talk about the routing tools and memory. And this is all with Spring. So as you can see, the demo here is going to be routing handoff tool use in the generator critic. In the flow, it's basically a customer issue arrives. The router then classifies that issue into 4 categories. If no single category dominates the evaluation, then it's going to be classified as a multi-use category. So this is one way to basically use an LLM to create branching points and also specialization points. So you can say, hey, this is it could be an HR issue versus a payroll issue. And you can say, hey, this is definitely an HR issue, let's go this way. But if somebody says, hey, I want to murder my boss because I haven't received my paycheck, they're like, this sounds like an HR issue and a payroll issue. But HR should probably be the first one. Huh? So again, routing intelligently in systems, it's the way to go. For example, in a lot of chatbots, our customers already had some sort of Q&A database that actually provide a lot of value. And sometimes it's a waste of time to basically have the chatbot just try to rethink all that stuff and try to do all this retrieval if you have already a Q&A database. So sometimes basically says, just route them to the Q&A system, or at least set the Q&A system as the primary retrieval for that specific conversation. And that is something that obviously is going to save you a lot of tokens, which seems to be now basically a cost center in most places. So I was supposed to run the demo. So let's do that. So this is basically, and I apologize, I went with Darth theme because I actually vibe coded the UI for this. I did the server side and I'm like, oh my God, I don't want to do another UI. So I vibe coded the UI and it loves dark themes for some reason. It's never, when I ask for a UI to any agentic coding assistant, it's always dark theme. Which I don't know, it could be a little scary. But in this case, one of the nice things that it did, it's that it basically, I said, hey, I am very slow at typing. I've been doing this for 30 some years, and I still type like a 6-year-old that just learned how to type. So it gave me the ability to basically, have a cheat sheet. So here is, so there's a chat. First let me show you. This is the actual data viewer. So in here you can see that. Let me close this. So you have your orders, and you have all your different entities in here. And when you click any of those, you can see actually the detailed view of that. And then the actual demos, and you can see there's all kinds of things in here. Products. So for each product, you can see the product ID, category, weight, an average review. So a typical e-commerce type of database. But then at the demo level, here is basically what would be used either by a customer representative that would basically be on the phone saying, oh, okay, the customer is experiencing this specific issue. So like I was saying, the AI assistant was very nice to me and gave me a cheat sheet so I didn't have to type everything. So I can basically do this message in here, and you can see that it's saying my order, some order hyperlinked, was supposed to arrive 5 days ago, and it's still nothing. This is the third time seller 42 has let me down. This is actually a very nice customer. Typically, I'm much more aggressive when it comes to automated chatbots. I know that when the AI, apocalypse comes, I'm going to be first in the list to be dispatched. So obviously, this is doing LLM inference, so it's going to take a little bit of time. But here, you can see on the left, basically, what happened. And you can see here that the customer issue arrived, and then the routing node basically kicked in, and it basically generated a draft. First, it figured out a route, so to classify that specific issue. And at the end of the day, basically, so you can see here, it's a delivery issue. The routing basically came up with that. So it could basically skip those. And then optimize an evaluation of basically how to respond to it. And what you see in the answer, it's basically multiple agents colliding and grabbing information from the database. So it's a RAG application, but it's multiple agents, each doing its own little RAG thing. And then composing an answer in this way. There is obviously a level of tuning where you can basically say, hey, don't be so pedantic. How many times do you have an agent basically tell you, it's like, you are absolutely right, I deleted your hard drive. I apologize. So, that's one of those things that prompt engineering, it's very difficult to make that, come out the right way. But again, this is basically what we saw in the slides. Let me go back to the slides for a second here, so we can highlight this. But you can see that the query arrives, the LLM classifier, so how does an LLM classifier work? Either you give it a prompt that says, hey, based on this input text, figure out which way to go, or you can pre-train a classifier using a vector database, where you can say, hey, it's a set of queries that should go to HR versus, and you use that to create embeddings in clusters of vectors. And then when an input comes in, you can quickly, rather than doing an LLM inference, which is expensive, you can just vectorize the input query and see which cluster of training data it's closer to, and then route it that way. So if you have very good examples of routing, then you can go with a vector database. If you don't have good examples, or it's a very novel or complicated routing equation, then you can use an LLM. And sometimes you can also use an LLM first, a cheap LLM, to determine whether the query is complex enough to require an LLM in the first place. So you can say, oh, no, just take it to the classifier to route it immediately. So this combination of different LLMs, vector databases, to basically do the cheapest possible thing that would result in a good outcome, it's very common nowadays. So the LLM in this case gives every specific subsystem a score, and then it basically uses that to do the right retrieval to basically create the answer. But it's still retrieving like the secondary match. It would basically grab some information from there based on the distance on that score coming in. So it could say, hey, the most important thing in here would be, for example, the triage specialist knowledge. And those are all stored also as memories in this Redis memory server. And it uses that to basically create a prompt that basically has the right priority data in it to create the right answer. So the routing in Spring AI, it's actually fairly simple when it comes to an LLM. You can say here that you can pass a prompt that says, hey, classify the customer message with confidence scores. Again, this is very fussy. So I prefer to basically use vector databases for this, and a pretty extensive training data sets, which give you faster routing and more deterministic routing too. But when you get started with this pattern, use an LLM. Use an LLM, get it working, and then figure out where can I get the data to basically train an LLM, a vector database router, to basically a semantic router, to basically make the same decision in milliseconds versus seconds. So this is all, from the get it to work to production. Okay, so the tool used in this specific demo, it basically follows the React loop. So basically, the React, it's observe, think, and act. We gave the LLM a set of tools. And the prompt basically says, hey, when you need to find something about the environment, about the different subsystems, use the MCP tool for the memory server. When you need to find specific data about a product, use the MCP tool for the product database. And by observing basically the observation in this case is basically finding specific things in the input query to trigger those tool calls. And then it basically just changes those calls and gets that data to create basically a more effective retrieval system. So we have a memory search, a memory store, and a working memory addition. Also, every time that you, for example, have a novel resolution for a customer issue, that will become a memory that you store. It could be a procedural memory. Like, for example, this is the steps that I took to help this customer. So when another service rep basically hits a similar issue, it would say, hey, here is the recipe. And that's a nice thing about LLMs, though. They can take that recipe that produced a good result for that service rep and templatize it on the fly and say, oh, for this customer, here is the same thing, but there's one specific thing that's different about this customer, and it adds that to that memory. Whether you collect multiple memories, or you basically then build a knowledge graph of basically how to solve this, or you turn it more into a mini kind of rule engine to basically says, hey, if this is the problem, these are the steps to take. All these things that the LLM is doing nowadays, with enough data and enough running time, can become deterministic, old school computational systems, either rule engines or mini expert systems. Therefore, the LLM just helped you basically train your system. So at the beginning, you're going to be tempted to put LLMs everywhere. I mean, LLMs is the new ketchup. It's like, oh, that's too hard of an algorithm. LLM. LLM here. That's okay at the beginning. Get things to work, show your boss, be like, oh my goodness, you're a genius. This is amazing. But eventually, a lot of those LLM blocks that you put in there would go away. And it's very likely that there would be one place where the system cannot live without an LLM, but most others are going to be easily replaceable. So a little bit of the code here, but I'm gonna move forward. The slides will be available. Tool calls in Spring, super easy. There's an at tool annotation, and you can create local tools. You can create MCP tools. So the MCP tools are auto-discovered by the LLM. A lot of people have different opinions about MCP. I used to be a little, for example, OpenAI functions used to be way faster than using MCP. But MCP is getting better and better and better. So now it's getting to the point that I'm like, yeah, I'm just going with MCP because it's a standard. At least we have a standard. MCP tool calling and how the LLMs is being able to change those tools. Specifically, if the tools return structure output, the system's quality have gone up significantly just because structure outputs in tool usage from the LLM's capabilities have improved greatly. So the generator critic at the end basically takes, it generates a draft response, and there's an evaluator LLM that basically, so this is kind of LLM as a judge, but we're kind of doing it at the agentic level. So rather than having, sometimes you have LLM as a judge in the cheap way, which is basically tell the same LLM in the same prompt. It's like, hey, can you check your work? And this is kind of like when I tell my kids, it's like, hey, follow the instructions. It's like you do the wash and then you put the stuff in the dryer soon after so it doesn't get moldy. And soon after to them, it's like 6 hours. So again, if you have the LLM judge itself in the same prompt, typically it leads to disaster. Two LLMs, sometimes not the same LLM. And the funny thing is sometimes you need a stronger, more powerful LLM for the judging than the LLM doing the work, which kind of defeat the purpose of basically trying to save tokens on the first LLM in the first place. So you're like, so this LLM, it's the right price, but it's too stupid. So I need to get a smarter LLM to tell this LLM, it's like, So yeah, welcome to my hell. But again, it creates a score and it stays in that loop until that score goes past a specific point so it can then answer to the customer or the service rep. So the generator critic, in here you can see basically it's a score the response on 4 criteria, 1 point each. And again, this is also very fuzzy. So this is all, again, first pass of a system. You're probably gonna start doing things, like we have systems where we do a lot of this, but we also have even regular expressions, finding key phrases, key words, things that finding ambiguity in the prompt. Sometimes you basically find ambiguity in the prompt, have something that can check basically how many contradicting thoughts are in a specific input query. And then use that to either do human in the loop or to basically bump up the LLM to like Claude, whatever, 4.5 and say, hey, I don't have any idea what is going on in here, so help me. So there's a lot of places where deviation here. But most of us at the beginning will go with the most powerful LLM so we can look good in front of everybody. You take all your crappy code and then you throw the most powerful LLM in there and you just basically be like, hey, look at what I did, So that is not gonna be, it's gonna basically very costly at the end of the day. So most of the systems that we worked on are using the cheapest LLMs you can possibly find, even open source LLMs in some places. And using just the expensive LLMs where it's crucial to have that reasoning capability. So think about that. Everything else around your environment has to be bulletproof because at some point, somebody's gonna tell you, it's like, hey, you can't use, Claude whatever 10. You're gonna have to use like GPT 3.5 or one with the dash mini at the end of it. And you're like, oh my God, panic ensues. So again, keep that in mind. So the pipeline, very easy to put pipelines together in Spring. You can see that I have my classification, I have my router classify the customer message, and then I can call the expert, which is basically the tool calling agent. And then I have my critic loop that basically keeps on, and again, this is very explicit. I have a max critic iterations. You basically just keep on going until this value goes above something and then spew out the answer. This, it's imperative. Like later we'll see that you can basically make this more goal-oriented. And on that note, let's move forward. So again, this is kind of what we saw on the screen. So now let's talk about multi-agent coordination. And this is where LangChain4j comes into place. In this multi-agent coordination, it's kind of like the same thing that we have in the Python world in LangGraph. So LangChain4j started as a sort of lightweight clone of LangChain, but then they combined different framework ideas. So LangChain4j is completely different than LangChain, the Python version. But LangChain, the Python version, has another graph-driven framework called LangGraph. In LangGraph, basically, it's used to orchestrate agent flows. So, and here the idea is that you can basically do a lot of different things. You can basically have a sequential chain. You can say basically run these agents one after the other and have them all pass their output to the next one. You can also do them in parallel. You can basically say fan out, do your work, and put your work in a center place, and then have something at the end, grab that, and do something else. So effectively, it's a sequential workflow of 2 agents. It just happens that the first agent is a combination of multiple agents working in parallel. So I'm gonna move a little faster through this one so we can basically get to the embabble part. Let me show you the demo here quickly. The peril with these demos is that basically they are LLM driven, so they're slow. So here is the second one, and let's do the supervisor. So those are the 3 styles that we have in there. So sequential, parallel, and then supervisor, it's kind of like I'll decide which agents need to do the work here, because they might not all be needed. And it has in the prompt some criteria to say, hey, if this is seems to be going this direction, then you might need this agent. So you can be pretty fussy in there, and then this supervisor basically, and we'll let it run. I'll switch back to the slides, and we'll come back to see it later. But again, this is all about orchestration. So if you work with workflow systems, with things that basically look like flowcharts, LangChain4j in LangGraph will give you that idea, where you can say, this is the start node, this is the node where the user enters the input. Here is a bunch of agents working in parallel with structure outputs going into this Blackboard type of shared data environment or the memory system. And here's basically how the workflow traverses the whole system. So in this case, I have 5 agents: an order analyzer, a delivery analyzer, a review analyzer, and a seller scorer, and a reporter. All those first 4 agents basically create specific structure outputs, and then the ops reporter creates a unified report of basically the whole scenario. In code base, you can see here it's the so every agent becomes an interface, and you can see here the agentic services class. You have an agent builder. You pass it the agent, a chat model, a list of data tools, and then the structure output that is going to create the key for the structure output. So here is the sequential one, where you basically would have agents running one after the other, and then all them writing their output to something called the agentic scope. So the agentic scope is just an implementation of what it used to be called the Blackboard pattern, which I think it would be more of a whiteboard nowadays, because blackboards is like you're a child of the 70s, chalk and all that stuff. Eat some, get a fever, don't go to school. You can find me later and I'll explain. So parallel fan out, again, very, very simple concept. Be able to fan out the agents and then aggregate everything in a join node, pass that to the ops reporter and create the report. The code actually is fairly simple for that. You can see that there's an untyped agent, parallel agent, and you can see that has sub-agents. So that's how I aggregate all those agents to run in parallel. Output key again, structure output. Pretty much, you should not do anything with LLMs without structure output. I think that should be one of the patterns. And you can see then that there's a pipeline, and then I can say, hey, the sub-agents now for this pipeline, which is sequential, is going to be the parallel agents that were aggregated, and then the ops reporter, which is the end of the process agent. And then the hierarchical delegation, so this is the supervisor one that we were talking about. This one, it would basically decide which agents to skip based on the severity of the issue, the data in the system, the reviews, the ratings of the seller, all those things. And it can basically say, so this is actually the most optimal thing to use in production. But it's the hardest one to figure out if it's going to work correctly. So start with sequential, then move to this, then go to parallelize the things that you can parallelize. So remember, parallelism, it's performance. So, early optimizations are the root of all evil. I can't remember, is that Raju? Who said that? Uh-huh. So, again, the supervisor, very similar code, but again, you basically look at the prompt. It says, you are an operations analysis supervisor. Only invoke agents relevant to the query. For delivery queries, prioritize delivery analyzer plus seller scorer. Always finish with ops reporter. So very simple prompt. So now let's talk about Embabble so we can close. So goal-oriented planning. And this is actually, like I've read a lot of papers about this before, but they were all academic. And then Rod went and basically built something. And this is actually really goal-oriented declarative agentic workflows. Not even workflows. You kind of don't have to really declare the workflows. So you basically declare what you want to do, In the system, you basically annotate entities to what they are, what they require, what they can provide. And then the system would basically assemble things on the fly. It sounds a little fuzzy, but it's actually much more precise because everything has typically a weight associated with it, a cost, a calculation that it's basically, typically you want to make it well known. Unless you make the calculation be an LLM, then you're added, non-deterministic behavior back into the whole system. But again, it's all about basically being able to outline your goals and let the system figure it out. Also, we can see here that the supervisor one ran, and you can see in the agentic scope the things that actually went into that Blackboard. So this is like a shared memory. Some of the things that went into the Blackboard actually came from the Redis agent memory server. So it's basically doing like a tool that basically uses another more sophisticated tool to retrieve memories. But you can see it got the query, order analysis, delivery analysis, review analysis, seller scores, and then the ops report at the end. All right, and let me see, this is what I wanted to do. So the last demo here, and let's see if the demo gods are with us today. And we'll do open mode. So open mode, it's basically and I'll go to the slides first so you can understand what open mode is. I might have done this in the wrong order. But again, for this, basically, given some operational issue, the system is going to plan a response. There's 7 actions. In the way that the goal-oriented action planning works, it's that the system itself is going to create a workflow on the fly based on the needs of that specific query. So it's not hard-coded anywhere. So there's deliberate planning where you can basically be much more specific and be like, these are always the steps I need to follow. Whether it does a lot or little on that step, it's up to the LLM, but it's still going to go through the step. And then the last one, it's, this is still deliberate planning. The OODA loop, it's observe, orient, decide, and act. So this is another basically more reactive approach. And then the one that I did there, it's the emergent swarm open mode. This is what Rod calls open mode. And again, the idea is that it's basically going to scan available achieved goals. So it's going to basically see what are my goals, what are the tools that I have, how can I basically put all this together to achieve one of those goals. And everything is based on basically a cost of how close, there's a number for achieving the goal and a number for how expensive things are, and you can basically optimize those two. So this is kind of like a route optimization system. And if you deal with basically anything that deliver goods in trucks, how to put the boxes in the truck, in what order, in what routes to take, this is just that, but at the software level for agents. Which is a pretty cool idea. If anybody worked with JBoss Drools in the past, so they had a sub project that basically did something like this, and I used to be all about that project, and nobody ever wanted to use it in production for some reason. I don't know. I think it was too pie in the sky academic for them. But this is the same idea, but done with LLMs, which I think makes it very, very valuable. And I think for a lot of systems, this is where the complexity it's very high. And the inputs are very fuzzy. This is going to be the best thing for those because it takes all that fuzziness and uses hard calculations and data lookups to basically make the decisions. It's not like, as an LLM, see what you can do for me. So this is, I think, a better approach for the enterprise. Much more visible, traceable, and I think this A planner basically it's the way to go. It's the way of the future. I think every framework is going to have one of these at the highest level of abstraction, and then for very specific things, you're going to keep on going down the layers of like, create my own workflow. So create my own have the flow chart magically be created, but with hard guardrails. Create my own flow chart. Or then really, basically pipeline everything at the code level yourself. So before we go, the quick decision framework here, route first, specialize later, sequential first, parallelize when it's slow, add a critic when quality matters, which is pretty much all the time, share state through a Blackboard or some kind of shared memory space. Agentic memory, it's evolving greatly, so go to Rafael's talk about agentic memory. You'll be like, whoa, I have no idea agentic memory was this complex. But it's actually the secret sauce to make multi-agent systems work well. Use a supervisor when not all agents are needed. That way you can basically save on compute cost, in LLM costs, in just general compute. Declare goals over workflows. So and even when you're designing, obviously, goal-oriented first, and then create your workflow from the goals rather than the other way around, which programmers, we tend to do that. Ground decisions in real data, the whole RAG thing, obviously, but on steroids. And human gates before irreversible actions, obviously. You don't want the LLM say, hey, this customer is angry enough, I'm going to send them 100 units of that thing that wasn't delivered. So yeah, just keep that in mind. In memory, it's a first-class citizen. Obviously, I work for Redis, and we are kind of like the memory guys. So yes, keep that in mind. And thank you.